Hello, and welcome to our final senior design presentation, where we'll be talking about our project, the tension web over slot die roll-to-roll system. We're Mechanical Engineering Group 48. My name is Gabriel Liebeck, and I'll be doing this presentation with Cody Allen, Vincent Bruno, Edward Dorsey, and Charles Mendelson. First, I'll be introducing the motivation behind our project. Several methods currently exist that allow us to produce photovoltaic cells. However, none have the exponential growth of efficiency like the newer, cheaper material known as lead halide perovskite. In the span of roughly a decade, perovskite photocells have seen an increase of efficiency from less than 5% to over 20%, which makes them the ideal candidate for large-scale manufacturing techniques. Current methods of manufacturing include spin coating and slot die coating. Spin coating deposits a perovskite liquid onto a small substrate and, as the name implies, spins the substrate to produce a uniform layer of liquid material. The unfortunate trade-off is that large amounts of material are wasted in the process as liquid spins off of the substrate. The second method that I mentioned, slot die coating, is the process of precisely metering the process fluid and dispensing it at a controlled rate while the coating die is precisely moved relative to a substrate. Slot die coating has a low operational cost and is easily scaled. The only current downside to this method is that no large-scale manufacturing technique currently exists. Now I'll be talking about the stakeholders. At the beginning of our senior design, we were introduced to our stakeholders, members of the Chemical Engineering Department at Drexel University, Drs. Jason Baxter, Nicholas Alvarez, Richard Carencross, and Aaron Fafferman. For this project, they asked that several needs be met. These needs include the following. The method we use to produce photovoltaic cells must be 1. Lab scale, 2. Must be roll-to-roll slot die coating, 3. It must be faster than the current slot die coater, and 4. It must be more efficient and less wasteful than spin coating. Now we have our problem statement. After meeting with the stakeholders, it was clear that our senior design must provide a solution to the biggest problem facing perovskite photocell manufacturing, which is scalability. The current lab method for producing these cells is a small Oscilla slot die coater, which produces cells at a rate of only a few centimeters per minute. Therefore, it was our mission to design and manufacture a system that would mass produce large quantities of perovskite cells efficiently and at a quick rate. Next is our approach. Our approach to this design is a roll-to-roll system that utilizes a slot die over tension web technique. The slot die, where liquid is dispensed, presses against the passing substrate and forces perovskite onto the plastic. The force of the ink as it leaves the die head produces a precise layer thickness of ink directly onto the substrate, where it can then move on to the next stage. The substrate used in our system is a thin polyethylene plastic only a few thousandths of an inch thick. Furthermore, the system includes 4 idler rollers that maintain the path of the substrate, a velocity motor to control its speed, a torque motor to control tension, and a control system that allows communication between the motors. The plastic substrate begins as a roll and is moved under the slot die head, where it is ultimately rewound into a roll as a finished product. Now we have our design specifications, and they are as follows. The system must not have a footprint greater than 66 inches by 18 inches by 27 inches. These dimensions allow the group to fit the final system into one of the Chemical Engineering Department's fume hoods. It's also important to note that the large length dimension that we were allotted allows for the future addition of a heating element that solidifies the perovskite liquid, helping to form its crystal structure. The design is also to be able to be broken down and reassembled should the need arise. And as was mentioned in the previous slide, the design must utilize a slot die over tension web technique. This is in opposition to an early design where we thought a slot die over precision drum may have worked, but that turned out to be too impractical. Another specification is the machine's ability to run at a range of speeds. On the low end, the system may need to run 30 centimeters per minute, and on the high end, the system may need to run 10 meters per minute. This speed range requirement is one of the main reasons why a control system was necessary for this design. And the final specification is the ability of the system to accommodate a substrate that is 5 centimeters in width. With the Oscilla slot die head mounted above the substrate, we know that a width greater than 2 inches cannot be dispensed onto the substrate. It is therefore unnecessary for the system to allow PET film greater than 5 centimeters on the rig.
As with most projects, As more progress is made, it becomes more clear what is possible and what is not, given resources such as time, ability, and budget. Our original scope included the roll-to-roll system frame along with the roller and motor control system needed to transport the web throughout the assembly. Initially, we planned to use a precision machined circular drum to maintain a precise gap between die head and PET substrate. After some research and requested quotes, we began to realize that this would be extremely expensive and risky given the level of machining precision required and the possibility of having to remake the necessary parts for future iterations. At this point, we decided that having a third party supply the die head and precision drum as an independent assembly would reduce the risk associated with designing it ourselves and mounting it properly so that it mates well with the rest of the system. Sourcing an entire die head precision drum assembly was found to be possible, but extraordinarily expensive. It was at this point that we switched to a different ink deposition method entirely, known as tensioned web over slot die. This method relies on the ink delivery pressure to create a gap between the substrate and die head. Oftentimes, the scope is also affected by unforeseen circumstances or events. The coronavirus pandemic is a perfect example of a situation that none of us could have ever predicted. Regardless, the team had to adapt and overcome the challenge. The pandemic placed severe limitations on our ability to carry out our planned project scope. Because it was no longer possible to work on physically demanding aspects of the project, we could no longer complete more electrical work or last-minute assembly. This included more motor and controller mounting. This also left us unable to work on programming our control system due to the inability to test and communicate with our physical motors. In the end, we were forced to remove the control system programming and remaining electronics work from the scope of our project. Our initial concept was a simplistic design that we would later improve upon. On the right, you can see a side view depicting the layout of our first design. The design took substrate material from a feed roller and unrolled it in such a way that it could be run along the machine drum to be coated. A pickup roller would then collect the material and re-roll it once dry. We incorporated torque motors onto the feed and pickup rollers and a velocity controllable stepper motor onto the precision drum. The stepper motor would allow for precise web speed control, and torque motors would apply opposing torques to keep the substrate taut as it moved along the dictated path. In our second concept, we expanded on our first and added some additional functionality. The idea for concept 2 was to allow for easy integration of a third-party precision drum die head assembly. As you can see on the figures on the right, we designed two options for die head location and roller placement. Beyond this, we sought to incorporate a feedback loop to measure any minor inconsistencies in tension that would arise over time and adjust for them. A linear active dancer was a mechanical feature that we thought to include to further ensure that the web was taut. The active dancer would use a spring or air cylinder to move a roller along a vertical axis to either lessen or increase actual tension. More idler rollers were also added to the rest of the design as a method of more precisely guiding the web as it approached the ink dispensing die head. Concept 3 was our final design. Our changes were based on the second option we proposed for Concept 2, but with slight modifications. Namely, this marked the switch from the precision roller deposition method to that of tensioned web over slot die. This concept was first fully fleshed out in the form of a 3D model using Creo Parametric. We completed the design down to each individual part that we planned on using in our physical design. Our CAD model was a perfect way to check dimensional compatibility before parts orders were finalized and machining had begun. It was with this concept that we set in stone our methods of constructing the aluminum frame, mounting rollers, motors, and bearings, and determining what material types would be best for our purposes.
There are three main types of rollers used in this design. The first roller is where the unused PET substrate is mounted. This is called the unwind roller. A stepper motor controls this roller to allow for control over speed of the substrate. The last roller in the system is where the finished product is collected and re-rolled. This is driven by a torque motor to control the tension of the system. Between these two rollers are idler rollers that are not motorized and help to guide the substrate through the machine. When it came to choosing the motors, they needed to satisfy a few constraints. They needed to be able to control the speed and tension of the system, which means that they also needed to be able to talk to each other. A stepper motor was chosen for the unwind roll because it has a large range of speeds and is able to maintain a constant velocity. A torque motor was chosen for the rewind roller because it's able to apply a constant force on the substrate and change as the width of the roll changes. Both of these motors also come with their respective control boards, which allow for signals to pass between them using a microcontroller. When it came to the speed of the motors, they needed to be able to fulfill the specification of a range between 30 centimeters a minute and 10 meters a minute. The stepper motor has a speed range between 0.02 and 600 RPM, while the torque motor has a max speed of 72 RPM at its maximum output. This means that the maximum speed of the substrate was at least 1,244 centimeters a minute, or 12.4 meters per minute. The stepper motor is able to reduce the speed all the way down to 0.02 RPM, which gives a minimum speed of 1.6 centimeters per minute. This allows the machine to reach all its required speed ranges and leaves room on either end for more adjustment. Determining the motor's output torque required calculations based on the PET material. The yield stress of the PET was found to be 40 megapascals, and with a thickness of 0.125 millimeters and a 5 centimeter width, the force required for deformation is 250 newtons. Taking a small percentage of this and setting it as the maximum force we would want to apply to the substrate yielded a torque of 3.5 newton meters, or about 31 pound-inches. This torque value is the maximum torque that the motors will apply to the substrate in order to avoid any deformation during operation. Because the thickness of the roll of substrate is changing, the motors may also need to output more or less torque. The frame of the machine needed to be able to have everything mounted to it and in a way that will allow for adjustments. Extruded aluminum was decided as the frame material because it is sturdy and there were many options available in terms of mounting hardware. The frame itself is 48 inches long, 22 inches tall, and 10 inches wide. This fulfilled the specification of being able to fit inside of a lab fume hood and left extra room for mounting the motors, electronics, and idler rollers. Motors were mounted directly to the frame, while the bearings for the rollers were mounted across from them using aluminum spacers. This modular and adjustable design allows for changes to be made to the layout of the system if future systems are added, such as an annealing process.
Ultimately, the design device never made it to the final testing stage. However, the design and construction of the device were very nearly completed. Multiple factors contributed to the change in design. Originally, the designed roll-to-roll system would incorporate a precision roller and a slot die head for ink distribution. Later, it was decided that a roll-to-roll system would control a PET substrate and design in a way that allowed the precision roller with a slot die to be placed onto the assembly in the future. Finally, a reduction in scope and financial restrictions would not allow for the purchase of a precision roller and slot die head altogether. It was settled that instead, a tension web over slot die method would be used. The electrical system for the design stayed relatively unchanged for most of the process. The motor selection was finalized after the physical design was finished. These motors were chosen based on the stakeholder needs and specifications. The first challenge for motor control was supplying power to each motor simultaneously. This required a 24-volt DC power converter and a 120-volt AC outlet. The next step was to connect the motors to a microcontroller that could send signals to each motor. This was a complex process that involved trial and error and searching through each manual for proper connections. In the end, torque and speed values for each motor was able to be controlled. For methods and materials, the mechanical portion included a frame constructed using 4-foot-long sections of extruded aluminum. It was important to establish structural integrity, so the choice to use aluminum sections benefit the structure and weight and strength. The aluminum will not oxidize in normal humidity the same way other metals such as iron or low-carbon steel may, thus making it a good choice for corrosion resistance. Most other large repeating components such as motor mounts, mounting plates, spacers, and brackets were also aluminum. The only steel components are the rotary shafts made from 1045 steel to ensure proper straightness, the idler rollers, and the pillow block bearings. For the electrical components, the two motors used for the control system are a stepper motor and a torque motor. The stepper motor allows for fine-tuning of the system speed, while the torque motor allows for the tension control across the substrate. Each motor was sold with a control module to route power and electrical signals to allow for communication. These signals all come from a microcontroller board that can be programmed to modulate signals based on the calculations from the computer. The motors and motor control modules are all powered from a 24-volt DC power supply. For fabrication methods, parts taken from Creo Parametric were made into orthogonal dimensional sketches to be used at the machine shop. All raw materials purchased from McMaster were machined at the Drexel machine shop. The guidance of the machine shop staff was also very useful during the manufacturing stage. Software. A critical component of the project was to understand how polyethylene plastic, used as a substrate, deforms under tension produced by friction in the rollers, the torque of the motors, and any other unforeseen contributions. In order to get an understanding of these forces, Creo Simulate Light was employed to quantify and graphically display the bending and deformation of the plastic under certain forces. The simulation of bending PET plastic shown in the figure shows how a section of PET bends around a steel roller under the applied load. In the case of the full model simulation, it was shown that the plastic performed comparably to the calculations completed at the beginning of this project. The major difference from the initial calculations is the existence of the rollers that created more friction than originally anticipated. This means that the tension added by the rollers was accounted for in the tension calculations. Therefore, the torque applied to the roll was reduced so that the increase in tension does not permanently deform the plastic substrate. Context and impact. Currently, photovoltaic module markets are dominated by Chinese manufacturers of polysilicon technologies. Between 2010 and 2017, the production of polysilicon in the U.S. fell from 29.1 to 11.3% of the global total, while China currently produces over 70%. As a result, PV market growth is constrained within the U.S. and expanding in China. Shown in the figure is the global PV markets in terms of installations. The industry has a high manufacturing capital expense, or CapEx, which drives up costs and limits profit margins. A solution to reduce the capital expense of PV in the United States is the development of printed perovskite-based solar modules. Printed perovskite film replaces silicon cells in the module. It replaces the need for silicon, solar wafer, and solar cell production. Perovskite PV are low-cost, organic, inorganic hybrid materials that can be produced using roll-to-roll continuous fabrication technique implemented by this project. This results in lower material usage than standard polysilicon manufacturing, which reduces raw material costs and environmental impact. PV has gone from being a specialized segment of the market to a mainstream energy source in the last decade. In order to tackle climate change, however, larger yearly volumes of PV must be produced.
Summary and conclusions. How far the project went. So we finished the frame assembly, which is pictured here. We ordered and machined the 4-foot-long extruded aluminum and finished the frame assembly, including the idler rollers positioned on top. We started the electrical components, but were unable to finish because of COVID. We do have the 2 motors used for the system, but they are not attached, and the motor mounts still need to be machined. Some challenges we faced. Aside from the challenge of working together during the COVID situation, we did have some difficulties throughout the process. The scope of the project, especially initially, was very complicated, so the planning stage was more involved to prevent having to correct any mistakes later on. The scope changes ate up a significant portion of our planning stage, and we were forced to restructure our plans to accommodate that. The designing was also affected by the changes in scope and the design changes, and we had to remake the 2-dimensional Keynote drawings a few times before even starting the 3D CAD model. When it came to the electrical components, none of us had much experience coding, so that was a struggle that went on into spring term and prevented us from really even getting into any of the electrical situation. For the group after us, we left the entire tension control system. We have the plans and the research and the handover files for the potential implementation of a linear active dancer, but we were unable to order the parts or even add them to the CAD drawings. Some of the parts that we have still need to be machined, including the stepper motor mount, the Delrin plastic cylinder, and control module mounts. Most of the electrical work still needs to be done, especially all of the coding, as mentioned before. We started working on the wiring of the motors, but didn't get past the troubleshooting phase. That will still need to be worked out by the next group. This is our bill of materials. Our total spent was about $1,800. We returned a few of these items, so this list may not be entirely accurate, and the group after us will have enough money to definitely implement a tension control device as we have prepared for. So this is a short summary of the year we've had in senior design. We were allowed a timeline that differed a little bit from the mechanical engineering timeline because of the scope of our chemical engineering project. The planning stage of our project was especially extended. So in the fall term, we proposed our project. We researched perovskite, roll-to-roll systems, and slot-die coaters. We used the research to solidify our design, which was agreed upon. In the winter term, our design changed again, which prolonged our designing stage. After a few two-dimensional designs, we were finally able to create a 3D CAD model in order to get approved for ordering parts. The parts arrived towards the end of the winter term, and we were able to machine them and put together a frame assembly, as pictured before. In the spring, we were overcome with a plague. We centralized all of our documents and completed files into a handoff folder to prepare the next group for a seamless transition of the project, since we were unable to finish building and constructing our prototype. Here are our references for the research we have done throughout the year. Thank you very much for the year in senior design, to especially all of our advisors for supporting us. Thank you very much.